Good afternoon, everyone, and welcome. I know that time is a commodity that not a lot of people have, so I want to thank you all for your time this afternoon. Welcome to another episode of the CODA webinar series, all about decommissioning. We're here today. My name is Rianne Gilbert. I'm the General Manager of CODA, and I'm thrilled to be here today with Raymond Ooi from Oleology, who will be walking through mercury removal technologies. As you go through the webinar today, please pop your questions in the Q&A if you have any, and we'll get to them after the presentation. We'll have a Q&A session, so please just pop them in there. So without any further ado, I would like to welcome Raymond and get him to share his screen. Thank you, Raymond.
All right. Okay. Thanks again, Rain, for the introduction itself. And honored to be able to share with you from Oleology on mercury removal technologies commonly used for the oil and gas decommissioning space itself. Yeah. So my role here is basically as the Director of Engineering. So I lead the engineering and the R&D development in Oleology itself. Okay. Moving on to the presentation itself. So what I've outlined over here today, I'll just start with talking about the industrial challenges that we have in water treatment and also disposal. And then later on, we're going to zoom into the areas of decommissioning on oleology capability in the areas of decommissioning, share a bit more about what this technology is all about. I'm sure you have seen it in the pre-read itself, but I have a small little video to show as well, and I'm just going to explain a bit more on how do we actually tackle mercury removal from waste or waste fluid or waste gas, could also be in the form of gas, that is coming off from these decommissioning activities, and how mercury can be actually separated prior to disposal. And last but not least, share a little bit more on some decommissioning deployment examples that we have actually deployed in the past and furnished some of our clients. So I guess in the overall sense of things itself, the challenges in the waste disposal or waste treatment activities itself, 5 key items to be highlighted here. Number one, it's variable. As you know, it's unpredictable waste in terms of the quality. When it comes to mercury itself, this whole issue of mercury speciation is always being discussed or always being talked about, right, in the industry. How does mercury present itself, whether it's elemental, colloidal, ionic, or even in particulates of mercury sulfate itself. There's also a challenge of limited space and weight. This is especially in the case of offshore facilities itself, especially when you talk about decommissioning. This is towards the end life of a facility itself, perhaps after 25, 30 years. The likelihood of having a deck extension done, for instance, right, to extend footprint or real estate, it's going to be very unlikely to get an investment decision on that. So most of the time we'll have to live with whatever space that we have left, in offshore itself, which is not much. Number 3 would be stringent discharge compliance requirements. As you know, compliance requirements are getting more and more stringent as it goes every day itself. Whether it's from oil and water, we have seen numbers dropping from 40 ppm to even less than 5 ppm in some areas as well. Again, likewise will be on the other contaminants like mercury. Waste storage, what do you do with the waste after you have processed through the treatment itself, and other logistical constraints, especially in the likes of a mercury removal pit. You hear the words MRU very often itself. This is the typical conventional system that is used in the industry that uses absorbents and media. What do you do with this media, and how do you handle this media after they become saturated with mercury? And obviously, with all this itself, eventually leads to high operational and also HSE risk, right? So knowing these challenges itself, but what is important for us to focus in the areas of decommissioning, like I mentioned earlier itself, if you go into the areas of mercury inventory and distribution, we struggle commonly to understand the distribution. So if you can't understand the distribution between, colloidal, ionic, elemental, and particulate as mentioned, we're not going to have a good ground to start off with the design, right? So in other words, you are not able to quantify the amount of mercury speciation. You know there's mercury in the fluid itself, but you are unsure how does it partition itself? And as we know, mercury, they like to accumulate in vessels and low points. You see a lot of this when you open up the vessel for vessel maintenance during turnaround. Potential discovery of mercury, especially late in life, changes of reservoir conditions, water cut, normally it's going to be too late for the facility to basically adapt to that change. In the areas of wastewater treatment itself, there's also limits to conventional technologies in terms of produced water, wash water, tank cleaning. The conventional technologies are mainly, in other words, you have a facility that has been operating over the last 25 to 30 years. The operating envelope has already been determined. The design has already been somewhat cast in stone. How are you going to basically react to changes in these conditions itself when you start to basically decom the facility itself? And contaminated scale and sludge management is also an issue. Mercury concentrates in deposits. They are accumulated over years of operation most of the time. And these itself generally requires cleaning and generate solids, which needs to be stabilized before they are actually disposed as solid waste. And then hazardous disposal and also handling itself. So with all these challenges in waste handling and also mercury decommissioning itself, it is important that we look or we approach each project at the very early stage itself, especially in the areas of mercury management, right? So what I've listed here is 5, I would say, front-end loading and value engineering opportunities to be identified. Number 1, start early. So screening and mapping of the mercury itself is critical. Understanding how mercury partitions itself, the quantity, what amount of elemental mercury, colloidal, ionic. It's important to have that mapped out early in the planning stage itself before you react to a waste that is actually seen during the decommissioning activity itself. The second bit would be on segregation. You would try to segregate your contaminated waste or waste that you see or you think that would have a higher quantity of, say, mercury compared to the other waste streams of just typically oil and water, for instance, if it's a liquid waste. That is that principle of segregation, of not to mix everything into one cocktail mixture itself and then having to treat all of them together in a single unit. Targeted treatment is also something that we looked at in terms of whether you go site-wide as a one single system that fits all, or you go into areas where you only concentrate on areas that's high risk. The areas where they are lower risk itself, you treat them on site. For instance, high risk is disposed, for instance, depending on the risk appetite. The treatment solutions, as I mentioned, it could be one size, or it could be coming out with a treatment solution that is robust, that is able to adapt to changes at site, whether it's fluid properties or whether surprises that you have whenever you open up a vessel, for instance. The goal is basically to have on-site waste removal from the wastewater itself. And by doing this itself, you are able to reduce the disposal volumes. Okay, so I think it's just a slide that we talk about in terms of having that front-end loading mentality early in the project itself, before you even in the planning phase of the project itself, before you start execution. So what does oleology bring into this picture here? So in terms of oleology capability in decommissioning, we are an integrated water treatment solution provider for the offshore and onshore decommissioning activities. We are basically practitioners in the area of providing solutions for tank flushing, pipeline flushing, and also produced water treatment itself. Because of the kit itself or the solution itself, as you can see from the screen on the far right itself, this is just an example of a filtration skid, roughly the size of a 20-foot container here itself. Because it's small and it's modular, it can actually be located in several locations itself. So the picture here on the left itself, we're just trying to depict where you can actually locate this skid. Can either be on the offshore platform itself, on the barge, on the work barge, onshore gathering, on the receiving side, or even down in subsea as well. Right. So this is how the skid looks like. Because it is small in nature itself, in the design itself, I'm going to tell you a bit more of what is inside these skids itself. But bear with me in terms of the overall size and footprint of the system itself. The picture on the left here is basically showing a picture of the entire system that is able to cater for the same treatment capacity of what the existing system was. So it is a picture of obviously an offshore facility. The largest square is showing the footprint of where the original water treatment system is. And with the deployment of the OLEOLOGY MySelect system itself, we're able to reduce the footprint just by having that 3 filter housing in the middle of the diagram itself. So it's the same treatment capacity, but done in a much smaller footprint itself. Because it's small, it's obviously easy to maintain, it's modular, and it is suitable to be used for decommissioning activities offshore. Okay, so what is the MySelect technology all about? Before we get into the areas of mercury removal itself, it's important to also understand that whenever we do flushing activities, prior to decontamination itself, there are bound to be, of course, being an oil and gas facility itself, oil in water itself. It could be sludge, it could be solids. So we go back to the theory of stage-based removal, right? The end goal, of course, is to get rid of the mercury itself, but we typically start with solids removal or pre-filtration stage itself. This is where we remove we protect the downstream filters with filtration system. It could be a media, or it could be also filter elements that have been designed and sized based on the particle size distribution to remove the solids, so that we keep the subsequent filters fresh and meant for their intended purpose, in this case for mercury removal, right? So that would be seen as a sacrificial stage itself to remove the solids. And then you got that big, large vessel in the middle. This is more towards oil recovery itself. When we remove the solids itself, there's also free and sometimes dispersed oil itself that is dislodged from the cleaning activity. So that itself can be removed by, the MAC basically stands for MySelect Advanced Coalescer. So what you have here is, instead of a filter cartridge, you have a coalescer media that enables oil in water to separate based on the principle of Stokes' law, right? So it helps slows down the velocity of the flow, it coalesces, and then oil, due to the difference in density, floats to the top, where it is then removed from the coalescer unit itself. So by having these two somewhat sacrificial stage itself upstream, you're able to protect the downstream filters for its intended use. So now going back into that element of mercury removal itself. So once the water has passed through these two stages itself, stage 3, 4, and 5, it's where mercury removal is actually happening, right? So stage 3 is more of addressing, again, it's a media filter that is being used. It's intended to remove the colloidal mercury, which we know that colloidal mercury binds to organic mass itself. And stage 4 is more of the ionic mercury, the dissolved mercury itself, which is in the salts, right? So that itself is also removed by another stage of filter. So this is a typical polyspun-based filter itself. But what you have here is a cartridge that is filled with media. So the operating principle is, I would say, different from all these 3 stages itself. One is more of an axial flow contact onto the polyspun membrane. The second one would be more of a media filtration, but we are able to fill the media into these tubes itself that would mimic a filter element itself to share the same connection end, and enables us to basically remove the ionic mercury itself. So these are media-based absorption. And then you go into the third stage itself. This is more of a elemental removal itself. I'm going to talk a little bit more on this elemental side of things as well. As you know, lots of the distribution of from a distribution perspective itself, we see, especially in produced water coming off from the well itself, a lot of them may exhibit a large volume of partition in mercury in elemental form itself. So this is more of a coalescer instead of a filter, right? So the same diagram that you have just seen, I've just explained earlier. Now you see them in a larger scale in a photograph. Here with this 3, 4, 1, 2, 3, 4, 5 stages. The first 2 stages on the colloidal mercury itself, there can be a different range or variety of filters that we may use depending on whether the fluid itself does appear to also have emulsion, especially the oil, or other dissolved organics like BTEX, phenols, and so on itself. So again, what we're trying to say that because you have filters that are interchangeable and the filter housing are basically standardized in that form, you are able to cater for fluctuations or provide a robust solutions in the event of uncertainties offshore itself. So what is MySelects? What are in the filters itself? Basically, every filter here is infused with a chemical itself, a polymer-based chemical itself, which is hydrophobic. In this case, they repel water, and oleophilic, and they attract oil. So what you have is basically a simple system, nothing complicated, no moving mechanisms and no pumps and whatnot. The technology is basically infused in these filter cartridges itself. And it's also important to note that when hydrocarbons bond into this oleophilic chemical itself on the surface, they are irreversible. So it cannot leach out from these cartridges itself once it's bonded to it, including the mercury in this case itself. Okay. So next, I'm just going to talk about mercury speciation itself. So because we understand the nature of each of the filter elements itself and the nature and the difference between each filter element, we are able to conduct speciation trial or speciation demonstration of the mercury itself. So how do we do that? Normally what we do is we will actually line up these three filter elements itself, starting with the colloidal type of mercury removal element, the ionic type of mercury removal element, and also the elemental mercury coalescer itself. So when you line them up together in series, and what we do is we pass water with mercury content, known mercury content at the inlet through the system itself. At the outlet of each of the element itself, we take a sample and we send it there. Basically, in terms of trying to understand or measure the speciation of mercury, is always a challenge in the labs itself, because as far as we know, going down the labs here in WA and also Australia itself, we are quite limited on the ability of trying to differentiate the different species itself. So what we can do is, what they can do is they typically measure total mercury itself. So because we know the nature and the operating principle of each of these elements itself, we go with the principle of elimination. So in other words, when you pass full direct water, raw water from the decom activity itself that has known mercury content, any mercury that has been removed or left after the first element itself, these are identified as organic mercury itself. And then likewise, when you pass through the second stage itself, because we know that the performer element or the performer media absorbs ionic mercury, and then so on. And then the third stage being elemental, right? So what we do is, at the end of the day, samples taken from S1, sampling 1, sampling 2, and sampling 3, they're sent to the lab. And because we know that they can measure the total mercury itself from the lab, we are now able to identify the partitioning of mercury through these three different species. So say from 100% itself, you may have, again, depending on water type quality, 55%, 45%, 5%, and so on. Okay, so just simply through the principle of elimination. Okay, so a typical process lineup for raw decom water is raw decom water that is collected from flushing, cleaning itself will first be passed through that pre-treatment stage, as I mentioned earlier. Could be media, it could be the sacrificial solid filter itself to first remove the solids. If it's oily, it will be passed through a coalescer to pick up the oil, the MAC coalescer. And from there on, it passes through that three-stage process as mentioned in the previous slide on removing the different mercury species itself. Next, in fact, this is a looping video just to explain. So what is this coalescer all about, for instance? The elemental mercury is removed on the third stage, as shown earlier. This coalescer, and it's not a filter. It looks like a filter element itself, but the way it works is actually it's a coalescer element itself. So what happens behind the scenes, in other words, itself? What's the operating? How does this system works, right? So it works in a system, it works in the principle of amalgamation itself. So what you see on these elements here is actually that is gold-plated. So it's a fusion of different metals that are braided together. And as we know, gold and mercury, they like one another itself, right? So when you contact with mercury or vice versa itself, amalgamation will form. So amalgamation forms, so this diagram on the right-hand side shows you that whether it's in gas or whether it's liquid, elemental into contact with the braid, they form amalgam. And over a period of time, the amalgam will start to coalesce, because think of it as smaller droplets of elemental mercury. When they come into contact with the braid, they start to grow. From the amalgamation itself, they will now start to coalesce. So subsequently, from coalescing itself, because it enhances in size, the droplet gets bigger. Now it starts to wick to the bottom. What we are trying to do here is we're trying to recover mercury, elemental mercury from the fluid itself. So this picture, I mean, this video, as you can see looping here itself, this is just, so think of it, you would inverse the other way around. This is just to show you that this fluid that we have here is a mixture of mercury in liquid. And when the moment it comes through in contact to the braid, mercury, even in this case, against gravity to the top of the braid. So it's very, you know, I would say it's a very ingenious way of doing it, or creating this device itself, because of how they measure mercury as well. As you know, a lot of mercury measuring devices are basically gold-based, right? So it taps into the principle of metal-to-metal bonding itself, mercury. And okay, so because this is a coalescer element itself, it doesn't get saturated itself, and whatever mercury that has been dislodged or collected onto the braid is collected. So think of it, inverse this the other way around against gravity. So what you have is now elemental mercury dripping and collected at the bottom of you know, the vessel itself or the filter. So these are just some of the deployment examples of how the technology has been deployed. Taking, for instance, a build that we have done in the past. So this big vessel, as I mentioned here, is the MAC, the MAC, the oil coalescer. And in these cartridges itself, in these filter housings, they are fitted with those cartridges as shown in the previous slides itself. So we will do a mix and match of cartridges itself, depending on the type of, the level of contaminants that we see in the water itself. But based on what you saw earlier, the 3 or 4 different cartridges, they will be lined up in each of these individual housing itself. One housing can have, you know, 10, 20, 30 number of cartridges, depending on the flow rate itself. It's scalable. Okay? So when they are used in combination, in other words, we are able to systematically remove contaminants stage by stage. That's the whole idea of it. Okay, and these are also some examples where we have previously deployed decommissioning solutions. So the first one is more of, remember that filter that was yellow in color earlier, which we call it HRM, hydrocarbon removal matrix, which has a polymer that is infused on it, that is oleophilic and hydrophobic. So if you infuse that into a cloth-like material, this example is used for pipeline cutting. So in this case, the client had wanted to basically cut the pipes subsea. And the problem statement is during the cut itself, what happens to the hydrocarbon that would basically release from this pipeline itself. So this was made into an absorbent mat itself that was taken down under the sea itself, in subsea itself, and was draped around the pipe itself. So these are just different ways of how the MySelex polymer can be used, just based on the principle that, you know, it's a magnet for oil, being oleophilic. It can be used in different forms and shapes, as long as there is a medium for it to be infused. The other few pictures here, it's more of the coalescer, the mercury coalescer, the MERCEP, as we call it, in action, where the mercury or elemental mercury itself that has been collected on the surface itself through that principle that I shared earlier, amalgamation, coalescing, and subsequently gravity drainage, they are now collected at the bottom of the vessel itself. So it's a very different technology if you talk about mercury removal. Like I mentioned earlier, it doesn't rely on absorbance. It doesn't rely on the absorption process itself. It's recoverable. There are no spent absorbance or no spent waste coming off from this itself. And the elemental mercury here is like I said, recoverable, and transported for disposal, or even subsequent reuse if there's a need.
There's a very
All
different.
right, so I think that's all I have from my sharing today itself. I hope what I've shared earlier does bring up a bit of thought process itself from how you can actually use it for each of your own use case itself. Happy to take questions about the presentation.
Okay, so
Great. Thank you so much, Raymond. We do have a few questions. So when carrying out the flushing activity, what mercury levels would you typically be targeting to be acceptable as clean and ready for decommissioning?
I think it depends. From our side, there's no real limitation because of the operating principle of the cartridges, as you've seen, also with the coalescer itself. The more mercury that comes in the inlet itself gets coalesced and gets collected and basically removed. There's no real saturation limit itself. It all depends on how much the client wants the discharge levels to be as per regulations. But from our side, it's more of aligning the number of stages that is required. Obviously, the higher the more stringent the discharge levels are, that will lead to more stages of filters being used.
okay,
Great. Thank you, Raymond. I had a question. I was wondering, and you may have covered this at the beginning of your presentation, how mobile is the technology, and could the treatment be undertaken at a port or a decommissioning yard, or does it need to be transported to your specialized plant?
Okay, maybe I'll just go back to some of these slides earlier.
Thank you.
Yeah. So I guess this question can be answered mainly from this slide itself. So as I mentioned, this is just an example of a 3x2. So in other words, it's duty standby, three stages of filtration. So think of it as in having the first stage to remove colloidal, second stage ionic, and then the third stage being elemental itself. This skid itself, each of these has 20 filters, 20 elements inside. It does a filtration rate of around 50 cubes per hour in terms of treatment capacity, and it can be loaded into a 20-foot container. So the size for this one is around 2.5 by around slightly less than 4 meters in length.
So what happens, Raymond, if the initial estimate for mercury is wrong? Do you then need to get a bigger unit, or what happens?
Yeah, so I think two ways of looking at it when we talk about estimates is wrong. Obviously, compared to a typical absorbent technology itself or absorbent solution, the amount or quantity of media or bed volume itself is obviously corresponding to the levels of contaminant. But from our end itself, it depends on which species. If you're referring to the ionic and colloidal, because these are filters, as I mentioned earlier, and it works on the principle of absorption, yes, they will require more frequent change because once the active sites are used up in the absorption surface itself, this media or this filter is considered as spent, saturated, so it has to be replaced. So it's a more frequent replacement of the media. But if you're referring to the elemental mercury itself, as shown in that video, if you recall, it's basically a non-consumable, in other words. So if you are not able to get the concentration right, which is most of the time the case itself, you can't depend on well testing data itself. There's no limitation to that because the more mercury that gets in contact with the coalescer, it forms, as you saw from the video itself, the amalgam itself, and then from the amalgam it drains and it's actually removed from the fluid itself. So there's no real, as long as it's drained, obviously mercury is not pooling up to the level of the element itself, then it should be fine.
Great, thank you, Ray. We've got another one here. Are there any examples that you can share to give us an indication of what mercury levels were before and after the filtration process is carried out?
The one that we have, in fact, that use case that what we had was mainly for the gas service. In fact, this example here is more of a gas plant rather than a liquid system, which we are currently doing some tests as well to also test the system in terms of trying to understand the full operating envelope of what it can do. But from the gas side itself, we had around 99.99% of removal itself. I think starting from, can't really remember the numbers off my head, but I think it had coming in at around 100 nanograms per cubic meter, if I'm not mistaken itself. Yeah. But it was a good outcome from this itself. It was a retrofit in this example itself. The elements were fitted into an existing filter coalescer. We took off the existing elements that they had prior, like you said, when you plan for design itself, it was never intended to have mercury coming into the plant itself, into the system itself. And what we did was we continued with the existing filter coalescer, but we just replaced the elements internally with this coalescer itself. So we are able to then remove the mercury before it goes to export.
Very good, very good. I have a three-part question, but I'll break it down into two smaller bits. Regarding the filtration skid process, what happens to the mercury saturated filtration elements, cartridges?
Yep. So the two stages that we mentioned earlier, these two, they will be saturated and then they will be disposed as a solid waste, as how spent filters are. Of course, with known mercury content in there, it will be handled as a scheduled waste itself. For this itself, the elemental mercury that comes off from the mercury element coalescer itself, they are collected and they are drained in the pot. We use something we call a Bethlehem container itself. This mercury is collected in that pot and then it is removed for disposal from site.
Does oleology plan and manage the disposal of these items and waste generated from the filtration process?
Not at the moment at this stage itself, because solely based on the volume and depend on the needs basis for the clients. But typically, we would supply these elements itself, and the disposal is managed by the client or the end user.
Yeah. So technical question here is somebody would like to know about the flow rate and the capacity of the individual filter bodies and the pressure vessel unit.
Okay, so go back to this. So for this particular unit here, it's operating around 10 to 20 cubes per hour itself, just so that you have a feel of the size and the footprint itself. Design pressure is 150-pound rating itself, designed for 10 bar. Again, we're not limited by this. As I said, the technology is inside the filter elements itself rather than the hardware in terms of the housing. So the housing can be designed for whatever pressure rating that is needed. In fact, we had even studied one example for the client to basically move these elements further upstream. I mean, this is slightly moving away from the subject of decommissioning itself, but say production itself, for instance, right? So you're moving it closer to the wellhead. Obviously, Christmas tree rating, 1,500 pound to 2,500 pound rating itself. All this can be done based on the design of the housing, but the elements, they work based on a delta pressure itself, a DP. As long as the DP, which we typically keep it less than 1 bar itself in terms of used versus clean versus dirty filters itself, yeah, we are able to keep it running itself. So if I answer that question on design pressure itself, can be any design pressure depending on need, can be fully rated. In terms of capacity itself, we will stage the capacity based on the number of filter elements. So depending on the use case itself, one filter element does between 1 to 2 cubes per hour. Like I said, these are all generalized numbers itself. We'll have to obviously look at other elements like the solids content and so on as well, right? So each filter element itself has a capture capacity up to, say, 2 kilograms of oil itself. Of course, mercury is going to be much lesser, but think of it as it's all embedded into the other co-contaminants like colloidal mercury into oil. And elemental mercury is just going to be coalesced and removed from the surface itself.
Good. Raymond, would the mercury removal equipment meet Australia's EPA regulatory requirement for shore-based safe handling, treatment, and management of mercury contaminated materials?
I'm not too, I'm not an expert in that area of, contaminant handling itself, but I think what we can say is we're able to get it off from the stream itself, from the process stream. That's number one. And number two, it's more of, what is available in the industry to be used. Like I said, the container itself, my understanding is Bethlehem containers are safe, they're sealed. They can be safely removed and decoupled from the site. And apart from the filters itself, it's going to be handled just like any solid waste that contains mercury itself.
Good.
Okay. There's lots of questions, Raymond. That's good to get so much engagement. So we have another one here. It says, how can all forms of mercury present within a pipeline be identified and measured, including elemental mercury, inorganic mercury compounds, organic mercury? And hold on. Wow, that's a very long question. Organic mercury, mercury vapor, liquid mercury, lots of mercuries.
Yeah, so I think the first three principles that we spoke about here is how can they be measured? We will use this method, as I highlighted earlier. It's a principle of elimination. So once you stage the sequence out in this way itself, through the principle of elimination itself, we are able to identify the breakdown itself. Right.
Good.
So the first one, like I mentioned, you will have organic base removal, because it's a hydrocarbon removal filter itself. We know organic mercury itself has the tendency to bind into hydrocarbons itself. So yeah, through that principle itself. So if you pass water through it with mercury, anything that comes off from each stage itself, hopefully say 100% goes through it is. First stage, probably you get 80% removed. Second stage, 15%. Third stage, 5%. So it's through that principle of elimination that now you categorically say that you got 5% elemental, 15% of ionic, and 85% of colloidal. So this is something that we can do in-house here in the lab itself, or it's just a small skid that is deployed to site, and it can be done at site as well, as that first stage of trying to understand the speciation of mercury.
Yeah,
good.
So here's a curly one. It may not be your area, but I'm going to throw it out there anyway. If it's not answered today, it might be a question that we tackle in the CODA Hazardous Materials Special Interest Group. But it's a subsea pipeline. Can you recommend methods of how a uniform cleanliness for the length of the pipeline be verified, other than sampling the waste fluids? This is a topic of interest as frequently requested by the regulator, especially for any leave in situ end states.
Good.
We have done some studies in the past for subsea itself. That's a bit more of a high level CFD type of study itself, computerized fluid dynamics, because I guess the key question here is always what is the starting level of the, say, even the oil level in the pipe itself that is left. Upon, yes, they must have done flushing over a period of time prior to decommissioning itself, but what is my starting point? So we were able to assess using CFD itself, based on the film, the thickness of the oil film that is left in the pipeline itself, and based on the flushing rate, are able to generate the amount of hydrocarbons that is actually removed from the pipe. And then from there on, we'll pass it through a treatment system like was shown earlier in that containerized unit, for instance. And then we are able to quantify the amount of mercury that comes off from there. So it's a bit of a combination itself, a bit of desktop, and yeah, at the end of the day, practical tests as well to be done at site.
Yeah, lots of interest in that area. Raymond, what are the detection limits, measurement uncertainties, repeatability, and overall accuracy of each sampling and analytical method?
Yeah,
it's a lot there. I feel like we would need to write a whole journal article about that.
Yeah, I think we're still relying on the lab. Again, not being a person from the lab itself, we are using atomic absorption methods itself, or even ICP, just from the slide here at the bottom here, method that we actually send to the lab to measure the mercury content itself. But I think from a repeatability itself for us is, yeah, we do a saturation trial as well. In other words, we start the system running, just passing the water, taking the samples at, say, time 10 minutes, and we repeat that over a period of every 30 minutes or so, which is what we have done. And that itself, we try to compare the differences in terms of the removal itself. So this is also another way that we use to determine the saturation point of this media itself. But yeah, we still trust the lab on the AA and the ICP method that they have. Yeah.
Yeah. Okay. It looks like the questions have slowed down. I'm just going to have another look. They're popping up in two different places. If you have any questions, put them in now. Otherwise, I will thank everyone for their time. As I said earlier, time is very important to everyone. So thank you for joining us at today's webinar. And thank you, Raymond and Oleology, so much for being our special guests today. Hope to see you all at the next webinar. And so I will just say thank you so much and good afternoon.